So hello dear students. Previously we have completed a brief description of static power compensator. Then we have completed a fixed capacitor thyristor controlled reactor configuration, which is of shunt controller. So second type of configuration is hybrid configuration, that is thyristor switch capacitor, thyristor controlled reactor type war generator. The thyristor switch capacitor and thyristor controlled reactor TSC TCR type compensator was developed primarily for dynamic compensation of power transmission system with the intention of minimizing standby losses and providing increased operating flexibility. So in case of FCTCR, what we are doing? We were controlling the thyristor control reactor by keeping the capacitor constant, or by controlling the firing angle alpha, we were just controlling the war capacitive war and inductive wars. So in case of TSC TCR, this TSC TCR is mainly developed to reduce losses and provide increased operating flexibility. So this is the basic diagram of TSC TCR. A basic single phase TSC TCR arrangement is shown in figure A. For given capacity output range, it typically consists of n TSC branches and one TCR branch. So in case of FCTCR, we were keeping capacitor constant and we were increasing n number of TCR branches. But in case of TSC TCR, we are increasing TSC branches and keeping one TCR constant. A basic single phase TSC TCR arrangement is shown in figure A. For a given capacity output range, it typically consists of n TSC branches and one TCR. The number of branches n is determined by practical consideration that includes the operating voltage level, maximum power output, current rating of thyristor volt, bus work and installation cost, etc. So the number of TSC branches depend upon all these factors, that is nothing but operating voltage level, maximum output, current rating, thyristor walls, bus work and installation cost. Of course, the inductive range can also expand to any maximum rating by employing additional TCR branch. So there is flexibility to also increase TCR branches, but there was no flexibility to increase FC branch in case of FC TCR. The total capacitive output range is divided into n intervals. In the first interval, the output power generator is controllable in 0 to maximum, that is QC maximum divided by n range, where it is QC maximum is total rating provided by all TSC branches. So n number of branches computes to maximum capacitive reactance or war compensation, that is QC maximum, where QC maximum is total rating provided by all TSC branches. In this interval, one capacitor is switched in by firing, for example, thyristor volt W1 or SW1, that is switch 1, and simultaneously the current in TCR is set by appropriate firing delay angle, so that the sum of war output of TSC negative and that of TCR positive equals capacitive output required. In the second, third and nth interval, the output is controllable in QC max divided by n to 2 QC max divided by n. From 2 QC max divided by n to 3 QC max divided by n, and up to n minus 1 QC max divided by n2 QC max. In these intervals or in this way, we have to keep switching the thyristor switch capacitors and thyristor controlled reactors. They range by switching in second, third and nth capacitor bank and using TCR to absorb the surplus capacity work. So in case of FC-TCR, we were switching the TCR and FC was absorbing the additional war compensations. In case of TSC-TCR, TSC generates the war compensation and TCR absorbs the surplus capacitive wars. By being able to switch the capacitor banks in and out within one cycle of the applied AC voltage, the maximum surplus capacity war in the total output range can be restricted to that produced by one capacitor bank, and thus theoretically TCR should have same rating as that of TSC. Since the work of TCR is to absorb the surplus capacitive or compensations, that means the rating of TCR should be equal to that of TSC. However, to ensure that the switching conditions at the end of the intervals are not indeterminate, the war rating of TCR has to be somewhat larger in practical than that one of TSC in order to provide enough overlap stresses between switching in and switching out war level. The ideally what I have said, you know, you know that the TCR absorb the surplus capacitive was, so the rating of TCR should be equal to TSC, but practically it is said that the rating of TCR should be higher than that of TSC. The war demand versus war output characteristics of TSC TCR type war generator is shown in figure B. As seen that capacitive war output QC is changed in step-like manner because we are doing the switching from QC max divided by n to 2 QC max divided 2 QC max divided by n, from 2 QC max divided by n to 3 QC max, and so on. That is up to n minus 1 QC max divided by n to QC max. That means we are switching the capacitor bank in steps. That's why the characteristics of or the war characteristic of TSC is in stepwise manner. As seen, the capacitive or output QC is changed in step-like manner by TSCs to appropriate the war demand with net capacitive war surplus and relatively small inductive war output TCR QL is used to cancel the surplus capacitive. So the net will be Q is equal to QC max divided QC max minus QL. In a way, this scheme should be considered as special fixed capacitor thyristor control reactor arrangement in which the rating of reactor is kept relatively small, that is 1 by n times of maximum capacity output, and the rating of capacitor is changed in discrete step so as to keep the operation of TCR within the normal range. So this is the function control block diagram of TSC TCR. A functional control scheme of TSC TCR type war generator is shown in figure. Here also we are going to change the TSC, or we are going to apply a control signal to TSC branch as well as TCR branch. In case of FC TCR, we were only giving the pulses to TCR branch, but in case of TSC TCR, we are going to give the pulses for TSC branch also and TCR branch also. The functions from the control diagram are: it determines the number of TSC branches needed to be switched in to approximate the required capacity output current with positive surplus, and compute the amplitude of inductive current needed to cancel out the surplus capacitive current. Control the switching of TSC branch in transient free manners. So one of the best advantage of this type of control is it gives the or it switch the TSC branches in transient free manner. That means the harmonic content will get reduced. Third, varies the current in TCR by firing delay angle control. So there are two types of controlling by giving the switching pulses to the TSC branch and by giving the firing angle to the TCR branch. The first function, there are three functions in this block diagram. The first function is relatively simple. The input current reference IQR representing the magnitude of requested output current is divided by amplitude IC of the current that TSC branch will draw at given amplitude V of AC voltage. The result rounded to next higher integer gives number of capacitor banks needed. The difference in the magnitude between the sum of active capacitive current, that is IC maximum, it is wrongly written, that is I16, it is nothing but IC maximum, make it correct over here, and the reference current IQ reference gives amplitude P of the fundamental reactor current required. So the whatever the reference current is generated is divided by the capacitive current, and after that it gives a value or integer. Depending upon this integer, we'll say that this much is the required capacitor bank or TSC branches. The basic logic of second function is either switch the capacitor bank when the voltage across the thyristor wall becomes zero or when the thyristor voltage is minimum. So how the switching is given to TSC branch, it depends upon the magnitude of TCR branch. If the voltage across thyristor wall becomes zero or the thyristor voltage is minimum, then switch the TSC branch. The first condition can be met if the capacitor residual voltage is less than peak AC voltage, and the later condition is satisfied at those peak of the AC voltage which has same polarity as the residual voltage of capacitor. The actual firing pulse generation of thyristor in TSC wall is similar to that of TCR, with exception that a continuous gate drive is usually provided to maintain continuity in conduction when the current is transferred from one thyristor string carrying current of one polarity, that is positive, to other string carrying current of opposite polarity, that is negative. So whatever the switching of thyristor switch capacitor, that is TSC, depends upon the magnitude of voltage of thyristor wall. For second condition, for first condition, it mainly depends upon the magnitude of AC voltage. If it is if the value of capacitor is less than the magnitude of AC voltage, then the switching of thyristor switch capacitor, that is TSC branch, is done. And in second condition, it mainly depends upon the thyristor voltage, that is TCR voltage. If it is minimum or zero, then the next switching is given. The third function is identical to that of fixed capacitor thyristor control scheme, which we have already studied in FCTCR. The operation of TSC-TCR type war generator with three capacitor banks is illustrated in figure 5.25. It is not necessary to consider this figure. Whatever the case is there is shown in the function diagram as earlier. Just the equation of the reference current or capacitive current is shown over here. The oscillogram shows the reactive current reference, IQ reference. The total output current, IQ, is equal to IC plus IL. The current IC drawn by thyristor switch capacitor bank and IL is the current drawn by thyristor controlled reactor. So in case of FCTCR, the total reference current, IQ reference, was equal to capacitive current IC plus inductive current IL. That is, inductive current was from TCR branch and IC current was from FC branch. So in case of TSC TCR, the net reactive current will be equal to IC, that is from TSC branches, that is N TSC branches, and IL, that is nothing but TCR branch. From the black box viewpoint, TSC TCR type power generator is similarly to FC TCR counterpart, can be considered as controllable reactive admittance, which when connected to AC system faithfully follows an arbitrary input reference reactive admittance or current signal. An external observer monitoring the output current generally would not be able to detect when the condition of transient free switchings are satisfied. The internal capacitor switching indeed would not be able to tell whether the war generator employs fixed or thyristor switch capacitors. So this is VI characteristics of TSC TCR. For 2 TSC is shown in figure is also identical to FC TCR, where VC max is voltage limit of TSC, VL maximum is voltage limit for TCR, IC maximum is capacitive current limit, IL maximum is inductive current limit, BL maximum is maximum admittance of TCR, BC is admittance of TSC, and BC max is admittance of maximum capacitive admittance. The response of TSC TCR type power generator, depending upon the number of TSC branches used, may be somewhat slower than that of FC TCR. If we compare FC TCR, the switching of FC TCR will be higher than as compared to TSC TCR, since in TSC TCR we have n branches of TSCs, also possible we have n branches of TCR. So the switching response of TSC TCR is somewhat slower than that of FC TCR. This is because the maximum delay of switching in single TSC with charge capacitor in one fully cycle, whereas the maximum delay of TCR is only half of the cycle.